Stage, Bob Hickman.
Hi everyone, thanks for coming. My name is Bob Hickman. I'm going to talk to you about the bits and bytes of bringing arcade classics to game consoles. So first, a little background about me and my journey. I'm originally from the UK, and if you listen really closely, you might still be able to detect a very subtle accent. I grew up playing arcade games with my older brother, and we were hooked. This got me into programming home computers, and I was the right age at the dawn of the UK's home computer explosion. Eventually, I became a software engineer for a living, and people started paying me for the stuff I'd been happy to do for fun. That's me there pointing at the monitor, as all good software engineers do. I'd always loved games, and eventually I got into the games industry through making my own games in my spare time and leveraging my network of friends who were already in the industry. I worked on several published titles for a third-party game developer. We made original titles, but also did a lot of ports. Then after I burned out from that insane crunch, I became tech director at Disney, working on a bunch of online and console games, including the very successful Disney Infinity series. Following my dreams, I switched business units at Disney and became a Disney Imagineer as a technology lead, and I worked on several advanced interactive attractions and lands, which was an absolutely amazing job. Hopefully there's a future talk there. And today I'm currently a software engineering director for an autonomous vehicle company, which is entirely owned by Ford, and where we're making the next generation autonomy platform for consumer-facing vehicles. Okay, so before we dive in further, I want to set some expectations since this is a pretty short talk. All of this happened a little over 20 years ago. The target hardware was modern then, but far less powerful than today's hardware. We might approach things differently today, and we can probably afford to take more shortcuts. This is, in part, a history lesson. There are several valid approaches, but this is how we did it. A lot of the decisions we made were based on the time that we had to deliver, the size of the team, and the availability of assets. Also, a lot of this is from memory, so there might be some bit rot. And this is just a taster. Come and find me later, or hit me up on Mastodon if you want to ask questions and get into the weeds. I'm more than happy to talk your ears off. Okay, so as an example, let's look at an original Pac-Man board's PCB board details. It's built around a Z80 CPU. It's running a blistering 3.072 megahertz. It's got 2K of dedicated video RAM, 2K of working RAM, and 16K of ROM to store the program and the graphics. The video circuit can output 288 by 244 pixels, but the monitor is mounted in portrait orientation, which means everything's rendered sideways. This is important to note as you're going to be deciphering the draw routines at some point. And it has a character mode with a hardware sprite capability. So let's talk a little bit about characters and sprites, for those who don't know the difference. Characters are mapped to the screen in 8 pixel blocks. In the case of Pac-Man, this works out to be 28 characters wide by 36 characters tall. Each character indexes an 8x8 image, and those characters can only appear on an 8-pixel offset on the screen. The character map usually makes up the background of the game and often doesn't change much. The entire background sometimes has pixel resolution hardware scrolling, but not on all devices. And sprites are normally larger, typically 16 by 16 pixels for the early games, but depending on the hardware, there can be a host of different sizes. Also, unlike characters, sprites can be placed at any pixel position and are fully independent of each other. And sprite clipping is usually free and taken care of automatically at the hardware level. So as a programmer, you don't usually need to worry if your sprite is halfway off the screen. Sprites have transparency and don't overwrite the background. There are some hardware limitations with sprites that you might need to be aware of, such as a maximum number of sprites on the same line. If you go over this limit, subsequent sprites might flicker or not appear at all. All right, so what does porting a game mean? Well, porting a video game is basically the process of converting a game so that it can run on a different platform. Usually involves making changes to the game's code, graphics, controls, and other aspects to make it compatible on your target platform. You can up-port or down-port. Down-porting a game to a less capable platform, it's often compromising on features and visuals. This was common during the home computer revolution of the 80s, with really depressingly awful versions of arcade games appearing on Spectrum, C64s, and early consoles like the 2600. Upporting, on the other hand, is porting a game to a more advanced platform and usually taking advantage of the additional capabilities. All right, so arcade classics, they're pretty small and simple. How hard are they to support? Well, it's a bit more effort than you might expect. All right, so how do we do this? Let's look at two common approaches that are pretty different. Firstly, the rewrite. So pros of this approach, since these games are old and popular, the gameplay design and the game flow is very well understood. When you're rewriting, it's going to be all new code, so you've got a lot of freedom in your implementation choice. You can write everything in a modern language, you can make it portable, etc. It's easy to integrate third-party libraries and frameworks to help speed up development. You can take full advantage of the hardware. Maximum performance since you're not writing from scratch. You don't include anything that you don't need. And if you want, you can add your own flair to it. Now on the downsides, you have to start from scratch. You can't really meet the expectations of hardcore fans, and they will complain. And no matter how careful you are, the pace and the difficulty are going to be subtly different from the arcade version. Because of this, it's easy to lose the essence of the original. And some of your audience will hate it. Why didn't they just emulate it? All right, so let's look at the other end of the porting spectrum, emulation. The pros to emulation, there's usually no need to rewrite the game logic. It's the most authentic arcade experience, keeping the essence of the original game. You likely don't need to remake graphics, or at most make minor changes to them. Possibly faster development time since you have all the code already. Potentially less debugging, at least from the gameplay logic side, because you're less likely to mess with any of that. And it's cooler, of course. On the downsides, you need to account for the different hardware. The arcade board had a bunch of custom chips and an archaic CPU. You'll need a solution for a different programming language. You're not going to write your game in Z80 assembler, are you? You may need workarounds for systems that don't make sense, like inserting coins and showing credits, etc. You might have to deal with dedicated analog controls that you just don't have on your target. You most likely don't have and can't get the source code. And there's a moderate amount of reverse engineering. You'll need to put some work into finding out where all the data is, what the functions are, and what they do. You need to try things out, make copious notes. A little bit more on that later. And it's generally less performant. The dedicated hardware was built for this game. Any translation that you do that doesn't take advantage of your target hardware will be less efficient. This is still true today, but you might not notice how many additional cycles you're wasting. Oh, and some of your audience will hate it. Still. Why didn't they just do a modern redesign and rewrite? All right, so on to our target hardware for this discussion. We're looking at Nintendo's Game Boy Advance. Isn't it pretty? It's a handheld battery-powered portable games console, and the specs are as follows. The CPU is an ARM7 TDMI running at 16.78 megahertz. It's slow by today's standards, but not too shabby. For memory, we have 32K of RAM, which is internal to the CPU, 256K of external RAM, which is on board but not directly on the CPU, and 96K of VRAM, which is internal to the CPU. The TFT display is 240 by 160 pixels in landscape orientation. Uh-oh. This is going to present a problem for portrait orientation games. Oh, and by the way, we worked on this before the GBA was actually released. So we had to build everything on an unreliable pre-production prototype dev kit, which was a bare circuit board, as you can see here, with a tiny screen on it that you couldn't see. And it would crash if someone so much as farted in the next room. So let's look at the games we're using as examples. Firstly, Namco Museum. Sold around 2.4 million copies last time I looked, which is pretty amazing. The games are Galaxian from 1979. This was Namco's answer to Space Invaders. It's in full color and a bit more challenging. Galaga from 1981. This still holds up as a superb shooter and is one of the most popular games of the era. I personally own one. Dig Dug from 1982, which is it's a tricky game. It's hard to get good at, but it's a pretty decent game. Pole Position from 1982, which is a really early arcade racer. And Ms. Pac-Man from 1982, the most popular game in the two products and arguably the most popular game of the early 1980s. The second title we're looking at is Pac-Man Collection, which sold around 1.9 million copies, so still pretty good. And the games are all Pac-Man themed in this one. They were Pac-Man from 1980. This is the game that started it all, but once you miss Pac, you'll never go back. Pac-Mania from 1987. It's sort of an isometric pseudo 3D version of Pac-Man, where you can jump over ghosts. Pretty good game, actually. Pac-Attack from 1993. This is a Tetris-style puzzle game with a Pac-Man twist. It's really the weakest one of the bunch. And Pac-Man Arrangement from 1996. A more modern version of classic Pac-Man with quite a lot of cool features. All right, since we don't have fully documented source code, we need to do some reverse engineering. So we'll need to get the code and the data from the ROMs, and possibly other chips such as GALs and PALs. We need to understand which blobs of data are code and which are graphics. We might want to reformat the graphics to work with our target console, most likely rotation in this case, probably some scaling or similar manipulation. We'll need a way of getting the assembler code executing on our target device, and we'll likely need to make some modifications to it. Mapping out where all the function calls are will help us find the routines that we need to make the modifications to. And initially, we'll want to stub out as much code as possible so we're not faced with a ton of errors right from the get-go. We can slowly bring more and more of the program in as we make progress with the port. Finding the sprite draw routine early on is super useful so we can intercept the calls and set our own temporary sprites to the XY positions as a way to visualize the logic. And then also finding the background draw routines also useful in a similar way. We can put our own messages there as we bring the game up, and we'll likely want to intercept and ignore or alter things in the final game, so the insert coin message, for example, or player 2 score, if we're doing a one-player game. And you can use the original arcade board if you have one, or you can use main for reference of what should be happening when the game's running. So how do we get the code and data? Well, you can download the ROMs from some nefarious website, if you have permission, of course. I'm not a lawyer, and I don't play one on the internet. You can use an EEPROM reader and pull the ROMs yourself from an original board and dump them. If you're doing this, label them the same as they are on the board and note the locations. This might help you determine what it is. Separating out the code and data can be a challenge, but there are some hints to help you. Firstly, you can look at the size of the ROM. The really small ones, 256 bytes or less, are likely to be from PALs or GALs, and they'll probably contain palette data. Look at the hex values and use your favorite web color picker to validate your assumptions, or do it in your head if you're elite enough. Hex editors are useful tools for checking ROM contents, and we can use it to see what different things look like. So code's usually pretty random, kind of random looking. Graphics typically have obvious repeating patterns, and text strings are often grouped together, and they're usually found in the same ROMs as the code. Code and graphics are typically, but not always, in separate ROMs. All right, so how do we make the original assembly language work on the target machine? Well, we can disassemble the ROM, clean up the output a bit, and then leverage the C's preprocessor macros to make C versions of each instruction. In this example, this is some 6809 instructions in the form of C macros. This is where the bulk of the work is initially, but the instruction sets are well documented and not too big. Here's some more C code. This time, there's regular C interspersed with Z80 macros. Now, there's potential for a lot of bugs here, and they're usually pretty catastrophic, but it means you'll find all your bugs really quickly. You may also need to deal with endianness if you're targeting multiple machines or the target doesn't match the source, and there are also robust ways of doing that too. All of this effort pays off if you're intending to port more than one game that uses the same CPU, so mostly it's worth it. All right, more reverse engineering. So make lots of notes as you go. There will be a lot of assumptions, and many will be wrong. So notes are a really good way of keeping your map of discovery as you refine your intuition about it and how everything works. Add comments to your code and confirm things. Add better ones than this. I'm still not sure why it was a great reason to draw the score backwards. Looking for known strings is another great technique for finding functions you might want to bypass or modify. Insert coin is a good example here. And going hand in hand with stubbing out as much as possible and slowly bringing things back in, Don't focus on output initially. Just have the code execute is a really big step in the process. Use your own debug sprite routine or the game sprite routine if you've already hijacked it, and then call it with interesting values you've discovered so you can see movement in real time. This is one of the more useful things you can do. Here we've got some of the sprites working, but the background's mostly broken, using the wrong characters, and it totally doesn't scroll as it should. But it is progress. Lean on the debugger or other tools to inspect the memory and look for known values, and you can do that by referencing a track mode on an original board. For example, like number of lives or score, etc. You can also guess a little bit at the XY positions, which shouldn't be changing if the player or the object isn't moving. And then don't worry about the correct graphics yet. That's a problem for future you, and he's an asshole. Use the background draw routines to print interesting values from memory to the screen. It's much more efficient getting info about what's going on if you can track interesting memory locations in real time. So, understanding and resolving the different hardware differences. So classic arcade games typically have all the hardware memory mapped. As we can see here, Pac-Man divides up its memory space into ROM, RAM, and then there's that small blue section there labeled control registers. Inputs and outputs are mapped to this control register address space. As you can see here, this example is the joystick. The joystick coin slots and service switch status is actually mapped into a single byte of memory. To discover this info, look for routines that read from memory locations rather than write to them, and that's how you'll find inputs typically. And then try and decipher what the code is doing with that data. Make notes and comments as you go along, and be prepared to update them. You're not going to be drawing sprites the same way as the original game does on your target game. So Pac-Man hardware just writes positions and attributes to a memory address, and sprites magically work. So you're going to need to find this sprite routine and hack it or intercept it to insert your own sprite routine that targets your own hardware. There should be data used by the routine that you can send to your new function, but just start with trying to match the X and Y positions so you can see the game playing before you get into the real hard stuff about working out what to do with colors and graphics. Finding the character draw routines can be easy if you look for known strings and see what routines are called using those strings' memory addresses. Again, you'll eventually need to replace this with your own function. If your target hardware doesn't match the resolution or orientation of the original game, you'll likely need to scale the values to make it work correctly. You can ignore this early on, but you'll only be seeing a partial screen, and if you're looking for something that's off screen, you might end up wasting a lot of time. Ask me how I know. All right, now we have everything running, and things are looking mostly right. We might need to boost performance, so let's look at some possible CPU-side optimizations. So the target CPU is faster, but it's still parsing a single Z80 instruction as one or more C commands. In tight loops, this can really slow us down and have the port running slower than the original. How do we target the right bits of code to focus on? Well, a useful hack is to change the background color when certain routines execute. So the sprite draw routine, collision detection, etc. As you can see in this example, we can get a visual representation of how much time each function takes to execute inside of a frame. And also, we can map function calls into a table with a couple of entries. You have the address of the function and the amount of times it's been called. We'll increase the count every time the function is called and let the game run for a bit. We'll end up with a histogram of function calls. So then we can use this to see which functions are called the most, and if they're simple enough, we can replace them with a more efficient C function instead. It sounds slower, but in most cases, this will be a performance boost. You can also time how long each function runs for, but for this, you'll likely need to use a profiler, which is a great tool if you have it, and you can easily integrate it into your workflow. Finally, anywhere the code is doing calculations on the fly, you can look at pre-processing these calculations into a lookup table for faster access. Think sine and cosine calculations, for example. So, we've done all that, but we're still not quite there. What other things can we do to help speed things up? Well, if you're planning on scaling any of the graphics and the target hardware can't do it for free, then consider pre-processing those so that you can do it, so you can just use the data natively. You can also pre-scroll graphics if you have no hardware support, but you do have plenty of memory to use. Chances are the target machine has some pretty nifty hardware, so learn about it and embrace it. Take full advantage of it. The Game Boy Advance, for example, has hardware scrolling on its background planes. It's got 4 separate background and 4 separate sprite planes that are interleaved. And the sprites also had hardware flip bits and transparency attributes, which can be a big memory saving. So that's the main part covered. Now there's a few loose ends to tie up. So let's look at pulling it all together. You'll likely want to pull several of these games into a single product. So for each of the titles we've been looking at, we had 5 games. There's some work here to ensure each game can be loaded without interference of the others, and that they can be reset cleanly. Additionally, you'll need to make some kind of shell menu that allows you to select which game you want to play. In our case, we also had variants of some of the games, scaled versus scrolling. Decide how the player is going to actually start a game and leverage the existing coin up and start routines to react to their input. Bypass parts of the code you're not using. It's a good idea to just stub these out until you're absolutely sure you don't need them. Again, ask me how I know. But several things that are appropriate for the arcade may not make sense for your port, such as 2-player mode, cocktail mode, and test mode. High score saving and recording. This is something you might want to add even if the original game didn't have it, and a lot of early games didn't. In that case, you want to find the bit of the original code that clears the scores during startup, and then add your own code there to restore your saved scores right after that. Note that we did implement high score saving in Namco Museum, but we took it out at Namco's request because the battery-backed memory would have doubled the price of a cartridge, leaving no margin at the $19.99 retail price. Okay, so we've looked at the general process for porting games, but there were some outlying problems we needed to address. I'll give a couple of examples of unique challenges we faced and how we made it work. So pole position was quite problematic. In place of the analog controls, we used accumulators which increased the effect every frame that you kept a button held down. This took a lot of testing to get the values feeling right. The downside is that you can't immediately brake fully right away. It takes a few frames. And likewise, you can't panic spin the steering wheel when you go into the corner too hot like we all did in the arcade. Performance was a real issue, partly because pole position has 3 CPUs. Before optimizations, we were getting around 10 frames a second on the GBA. We used the histogram technique and the routine replacement tricks, which got us a decent speed increase. Some more profiling showed that the horizon function was really slow, and it was drawing it in real time. Instead, we pre-processed the horizon into sprites and scrolled them for free in the hardware. With this, we were finally running at 60 frames a second most of the time, but would occasionally run over into the next frame, making the game look and feel really choppy. This was remedied by decoupling the game logic from the display update code. Every time the screen update took too long, we ran the game logic twice. You can tell if you know what you're looking for, but otherwise it made for a pretty smooth play experience. So Pac-Mania was another title that gave us a lot of problems. We used a similar solution to improve the slow background scrolling, switching to pre-processed backgrounds and hardware scrolling with multiple planes. By far, the biggest issue was that all of the graphics didn't fit in VRAM. So you can see here that the colors are all janky and flickering, etc., which was a huge problem. So I calculated that there was still enough VRAM to show all of the graphics needed for any single individual frame. So I devised a dynamic on-demand sprite and palette DMA solution so that only the sprites and colors needed for the current frame were copied into VRAM, and all of the indexes were dynamically fixed up to match. This is what it looked like after optimizing those two things, which is a huge improvement, as you can probably see. You can also see that I was printing values to the screen here, yay, following my own advice. And it appears to be showing that I'm only using 60 to 70% of the total time available in one frame. Yay! Both titles were a real rush to market with short timelines and thin margins. We were able to make 2 really faithful and fun products for the Game Boy Advance. I'm still immensely proud of what we achieved back in the day. And that's all I have for now. If you'd like to learn more, come and find me for a chat or hit me up on Mastodon. Thanks.